Okay, we will finish up this chapter, virtualization. Yesterday we started talking about it. We said that virtualization and virtual machines has lots of advantages, and we talk about two types of hypervisors, type 1 and type 2 hypervisors, and this way our overall system becomes more reliable because this type of hypervisors, they are much more simpler than uh, any regular operating systems. So less number of lines of code means uh, less chances of having a bug in a in this software. So that's why we say that software related crashes for this whole overall system is minimal compared to this kind of a system. Okay, so we said that they are reliable. We have lots of savings on hardware, electricity, and rack space. They are cheap, less hardware. And this is a very important advantage, actually. Migrating virtual machines is much simpler than migrating processes on regular operating systems. Okay. And development is much easy, etc. Lots of advantages. We talked about this last time. And requirement for virtualization, how virtualization should be done is something we talked about it. We especially stressed out the importance of efficiency. Okay, and we said that much of the code in virtual machine should run without intervention by the hypervisor. We talked about this, and I think we were around here, right? Yeah, we were talking about type 1 and type 2 hypervisors examples. The most common hypervisors that we use is, I guess, this one and this one. Okay, they are type 2 hypervisors, and the corresponding hypervisors in type 1 category is these. These are all in virtualization with hardware support. So these hypervisors, they get hardware support um, from the CPU, from the hardware. But before that, we had these kind of hypervisors, VMware Workstation, and they didn't get any hardware support, and we will talk about it in a few minutes. Okay, but before that, let's talk about this para virtualization. This is regular true virtualization, okay, system. You have Windows, regular Windows operating system. You have processes running on top of them. Neither the processes nor the operating system doesn't know about the hypervisor. They think that they are running on a regular hardware. Okay, this type 1 hypervisor is responsible for making prepare this virtual environment. Okay, some people say that since virtualization is such a common and important thing, why don't we why don't we modify our popular operating systems such as Linux and Windows in a way that they know that they are working in a virtualized environment? Okay, so when they need to reach the hardware, they make a kind of a hypervisor call to the hypervisor or microkernel here. Okay, so this one becomes kind of a more abstract operating system. And this Linux knows that it doesn't have right to access the hardware. So it is making a hypercall or hypervisor call to this microkernel. This Linux is modified. Okay, so it makes things a lot easier. It makes things a lot more efficient because I don't have to do the trapping. Okay, because trapping is expensive. I don't have to produce this interrupt and etc. And Linux knows that it is in a virtual environment. It is not heavily modified. It is very slightly modified Linux. And I can run many copies of this Linux on this microkernel. Everything is as before. This is called para-virtualization. Okay? It is called para-virtualization. And para-virtualization is a common thing. Um, it offers a set of hypercalls which allow the guest to send explicit requests to the hypervisor, and guests use the hypercalls. Okay, and this whole thing more simpler and faster. Everybody knows each other. You might say that this is the against the idea of virtualization. In virtualization, the guest operating system doesn't know that it is running in a virtual environment. Yeah, that's true, but the advantages of uh, advantages of whole virtualization comes with the para virtualization too. Okay, I save on hardware, electricity, etc. Migrating is easy again. Okay, this can and this one is all valid. So other than the um, guest operating system doesn't know that it's working in a virtual environment. Everything is valid. Okay. Um, so we talked about this para-virtualization thing, and of course it's a type 1 hypervisor, but it could be type 2 hypervisor too, but you don't have much choice here. Okay, and now let's talk about the difference between this one and this one. Virtualization with hardware support and virtualization without hardware support. That is that is that is that is uh, you are in an environment where you are in an environment where there is no virtualization support. Okay, so hypervisors, they say that either they're type 1 or type 2 hypervisor. They make sure that no sensitive instructions in the guest kernel code. Okay, so uh, if I have this guest operating system, uh, it is running code, of course. It is running non-sensitive code on the directly on the hardware. That's true. But if it tries to run the sensitive code on the hardware, then that's a problem. So the hypervisor itself needs to make sure that no sensitive instruction is in guest kernel code. So if I don't have hardware support for virtualization, this is what you do. If this is my code of the operating system, there is a piece of code where you have a number of lines and there's a jump instruction at the end. Another piece of code, a number of lines, and there is a jump instructions at the end. Okay. So these kind of hypervisors, they take these codes, okay, these pieces of codes, where at the end there is a branch. It takes them, okay, it rewrites them either on the fly or offline, usually on the fly. So it rewrites the code one basic block at a time. So that by rewriting, what I mean is, by rewriting, what I mean is, it makes sure that the guest kernel code doesn't have any sensitive instructions. So it either emulates those sensitive instructions or it replaces them with hypercalls. Okay. So basically, this is what is on dynamic translation and emulation. If you don't have any hardware support for virtualization, this is what you do. You translate and emulate your guest operating system's code so that it doesn't include any sensitive instructions. Okay? It may sound expensive, it may sound too much work, but if it is done cleverly, okay, they are typically usable, and sometimes they are faster too. They are faster than the original. And these translated blocks are cached. So if I need to use them again, I don't need to do the translation. I don't need to do the translation again. Okay. So this is how you do the virtualization without the hardware support. Okay. How about the hardware support? What do I mean by hardware support? Hardware support is this. Hardware support is this. If this hardware, let me show you. Remember the figure I drew yesterday? Where is my figure? Yeah. Remember what I said yesterday? Uh, if let me erase these red stuff. Okay. This is type 1 hypervisor. This is my operating system. These are my regular processes. General hardware, everybody is using it. But this protected hardware, privileged hardware, only type 1 hypervisor is using it. If the operating system here is using a privileged instruction, it causes a trap by the operating system. Operating system produces a interrupt, and that interrupt is handled by the type 1 hypervisor. Okay, so this is what happens. The operating system uh, causes an interrupt, but it doesn't know that it is causing an interrupt. And that interrupt is handled by the type 1 hypervisor. So it is kind of like this. Okay. So operating system doesn't know that it is causing an interrupt, specialized interrupt, and that interrupt is handled by the type 1 hypervisor. So in this case, the hardware knows that there is a hypervisor and all the rest is regular processes. Whenever one of these regular processes is using privileged hardware, then it will let the type 1 hypervisor know. So this hardware is designed that way. So this is the minimum of the hardware support for the virtualization. Okay, when you execute your instructions. Of course, there are other support mechanisms, such as the virtual memory support, input-output support, peripheral support, and etc. We will talk about them. Okay. But if you don't have any support, if you don't have any support for virtualization in your hardware, it is still possible to do virtualization. And in fact, it is only maybe 10 years, maybe 15 years. I think like 15 years ago, Intel has introduced this virtualization support usable by other operating systems. So it is in the PC world, it is kind of new. Of course, virtualization is as old as the mainframes. In 1960s, IBM had IBM had virtualized operating systems running. Okay, the theory. Everything was set in 1960s, 70s. But in the PC world, because our PCs are so weak, they are the CPU wise and the memory wise, they are so insufficient that we couldn't think of virtualization. Okay, when they became powerful enough, then virtualization took off. And without the hardware support, we had this kind of VMware workstation. We had these kind of hypervisors. Okay, good. So we talked about this. Okay, virtualization support is important, but that's not the only thing that we can do. We can virtualize the hardware that doesn't support the virtualization directly. Okay, and the Type 2 hypervisor, I mean, so far we used only Type 1 hypervisors. Type 2 hypervisors are valid virtualization tools. Okay. Uh, exact techniques required for Type 2 hypervisors to manipulate the hardware at the lowest level. That's why Type 2 hypervisors are kind of like this. Hardware, there is an operating system. Type 2 hypervisor actually needs to access privileged part of the hardware directly. That's why you left a hole in the operating system layer so that Type 2 hypervisor can access the hardware. Okay, so that's why when you install your VMware, okay, when you install your VMware or KVM, whatever it is, it takes some time to install. It takes a few times to reboot your computer. Why? Because I am trying to make this kind of an hole. So definitely, Type 2 hypervisor is not a regular process like A3 or A4. A3 and A4 has no privileged access to the hardware, but Type 2 hypervisor has. Okay, Type 2 hypervisor has. That's why most of the time, Type 2 hypervisors are more complicated because it has to know the details of the hardware and it has to know the details of this operating system. Sometimes it makes a system call, sometimes it directly accesses the hardware. Okay, so most modern Type 2 hypervisors have a kernel module operating at the lowest level. Okay, good. Any questions so far? Okay. You might think that, I mean, this hardware support by virtualization support is handling everything. Whenever this operating system, guest operating system, is causing a trap, okay, type 1 hypervisor handles it, and this one continues. It sounds okay. It sounds okay. But trapping is expensive. Why? Because the hardware has to stop everything. It's an interrupt, right? We like interrupts, but we know that they are expensive because it causes a context switch and that kind of stuff, and etc. Okay? So people have realized that trap and emulate used by the virtualization support causes lots of interrupt handling, lots of traps, and they are very expensive on modern hardware. What do we mean by modern hardware? They they are not that expensive in primitive hardware, but for modern hardware, handling interrupts or handling traps is expensive. Can anybody explain why?
Because on modern hardware is very fast and context switch takes some time. On older hardware, it doesn't it doesn't make much more difference. I think by means of
Why? Yeah, tell me why. What you are saying is true, but why it is more expensive on the modern hardware? I mean, speed is the same thing. I mean, when you handle a trap on the old hardware, it is the same speed that you are running your instructions.
yes,
Why?
but on modern hardware, you are running instructions more faster than old hardware. So it doesn't make difference on old hardware, but it became a bottleneck on modern hardware, I think.
No, not exactly. Try again. There
Okay.
is, try again. There is one more big difference between old hardware and new hardware. Yeah, that's true. It is faster, maybe 1,000 times, 10,000 times. But I mean, if it is fast, then I can handle the trap fast too, right?
Yeah, actually.
Yeah. So what's the difference? I mean, on modern hardware, there is another big advantage other than the speed. Why context switches are expensive? We keep talking about it, right? We said that context switches are expensive and expensive. Why are they expensive?
Because we refresh the table and rewrite the table page,
You
table.
mean the page table, right?
Yes.
Well, previously we had the page tables, but nowadays our page tables are much larger, TLBs. Our caches are much larger, right? And our pipelining, okay, our pipelining is much more complicated. When a trap happens, we have to invalidate very large amount of cache data, very large amount of TLB data, and we have to stop the execution of the pipeline instructions. So these will cost more. They will cost more. So stopping all that processes, invalidating the cache, repopulating the cache and the page tables, it takes much more time. That's why for the modern hardware, traps are so expensive. We like to stay away from them. So this brings us to this one. We say that although we have virtualization support by hardware, some hypervisors they prefer to rewrite the code so that rewrite the code of the guest operating system, translate it so that it doesn't cause any trap. Okay, so with binary translation, translated code itself is sometimes faster than the original code that involves lots of traps. Okay, that's why even though we have the virtualization support, some hypervisors don't use some part of it. Okay, good. Do you guys remember? Do you guys remember the microkernels? What was the advantage of microkernel? Yes, Abdullah.
It was smaller in comparison to a regular kernel, so probability of including a bug is much more smaller.
Exactly right. That's the definition of the microkernel. Some people say that aren't the hypervisors like microkernels? Okay, this is like an operating system, right? Very simplified operating system. It includes only the necessary services to use the privileged hardware. The rest of the stuff is in the operating system. Okay, so maybe the hypervisors are microkernels. We can consider them as microkernels, especially with the para-virtualization. Now this modified Linux, it knows that it doesn't have access to the hardware. It has to make hypercalls. And those hypercalls are handled by this specialized hypervisor. So this is another way to look at the microkernels. Okay, so they are kind of doing the virtualization for you. Okay, and if the interface for this microkernel is standard, then I can put any type of modified Linux or Windows or Mac OS 10, whatever. Okay, so this is another way to look at the microkernels. Okay, so we looked at those, and basically this is available. Okay, so this is virtual machine interface. If all the operating systems behave that way, okay, so if I put a layer of software between this virtual machine interface, Linux or some other operating system, I can run it directly on the hardware. Okay, there is a library here. There is another library to make it possible to use it on this VMware or Xen hypervisor. So if I put this library under this virtual machine interface Linux or modified Linux, then it can run anywhere, right? It can run either on basic hardware or on VMware or Xen or whatever. Okay. So virtualization, since it is in software, there are many possibilities that you can think of. And so your task is from now on, write your operating systems this way with the virtual machine interface implemented, then your operating system can run in any environment more efficiently with the para-virtualization technique. Okay, what was the advantage of para-virtualization? It is faster and more efficient. Okay, so far we kept talking about CPU virtualization. Okay, if there is if your CPU supports virtualization, it causes a trap if somebody executes a sensitive instruction. Okay, and that trap is handled by the hypervisor. That's the support of the virtualization by the hardware for the CPU part. How about the memory? Memory has to be virtualized too. Okay. So how do we do the virtualization? Well, we know that for the memory, we're already using virtual memory. Okay. There is a page table for each process. And the operating system has a page table too. And page tables and physical to virtual address translation is handled by the hardware. So the virtualization support in general for each virtual machine by the hypervisor, it creates a shadow page table. Shadow page table is just a copy of the page table, and it maps the virtual pages used by the virtual machine onto actual pages the hypervisor gave it. Okay, so hardware supports this. In addition to guest virtual addresses, okay, now we have the guest physical addresses. It is kind of confusing. So guest virtual addresses, guest physical addresses, but those guest physical addresses are not real physical addresses. Okay, they have to convert it back to the host physical addresses. Okay, host physical addresses are real the physical addresses. Our guest physical addresses are again virtual addresses. So there has to be some kind of virtual to virtual than the physical translation. And this is done by the hardware. Remember the Intel structure, Intel architecture for the 4-level page tables. Okay. So when this happens, when you translate this level 1 offset, okay, guest pointer table to level 1 page table, then you do this translation, again, nested page tables, and you produce a physical address, and you get it from the second level, you do it again, etc. So this is all done. This is all done in hardware. Hardware gets much more complicated. So don't think about virtualization support on the hardware as simple trapping, okay, of the sensitive instructions. You have to support your memory too. Otherwise, your processes will not run correctly. Okay, so that's the very simplified, very simplified explanation of hardware support for the memory virtualization. Okay, good. Sometimes this paging becomes a problem. Remember, I kept showing you this. I kept showing you this all the time. For some reason, after I/O, I didn't show you. Okay, let me go to my, yeah, this one. No, 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 no. I think this one was okay. No, this one was okay. Okay, as you see, even though I have 16 gigabytes of memory, okay, only 4 gigabytes is available. and I am not using much memory right now. Okay. If I had only 8 gigabytes of memory on this computer, my computer would have run the same speed. Nothing would have been any different. And I would have maybe 2 or 3 gigabytes of memory available too. So why is this happening? I mean, if I give more physical memory to the operating system, it uses it up. It does it because it tries to keep fresh pages available all the time so that it can do the demand paging in a more efficient way. So if you do the same thing for these operating systems, guest operating system, they will try to use the whole available memory. And that's not going to be a good thing. Okay? They will try to use the whole available memory. And sometimes this hypervisor, type 1 hypervisor, they put these kind of fake processes in guest operating system, which doesn't do anything but they just use memory. So this type 1 hypervisor adjusts the required memory for these processes, B processes, so that these two processes are using their fair share of memory. This is called ballooning. So they inflate these processes or they deflate these processes depending on how much the hypervisor wants these guest operating systems use the memory. Okay, so you have to play these kind of tricks. You have to play these kind of tricks with the guest operating system when you manage your memory. Another topic is I/O virtualization. We have to virtualize our I/O devices. Okay. Each guest operating system thinks that it owns the entire disk partition. So you might think that, well, then make a new partition for each. Make a new partition for each virtual operating system. That might be a good solution. But what happens if you have hundreds of virtual operating systems available? Okay, I cannot create hundreds of partitions. That would be expensive, unnecessary, and that wouldn't be dynamic. So the solution is for hypervisor to create a file or region of the actual disk for each virtual machine's physical disk. It's like your homework number 3, where you are creating basically a file system on a file, and the hypervisors do the same thing too. Okay, hypervisors do the same thing too. Good. So this is about I/O virtualization, especially for the disks. How about the other I/O stuff? For example, we have the I/O port space, right? I/O port space. Each device has a address, I/O port address, and the operating system reaches those addresses, manipulates those, and gets the data from the hardware and puts the data to hardware. But now I cannot let the operating system access those port spaces directly. I have to manage this too. Okay. So I get the hardware support. It is IOMMU. Remember the memory management unit? It during the runtime it translates all the memory virtual memory addresses, the physical memory addresses. Now I have the IOMMU. It virtualizes the IO the same way as the MMU virtualize the memory. And IOMMU can handle DMA addressing. DMA chips, they know nothing about virtual addresses, they know the physical addresses, okay? And somebody has to manage this because my whole operating system is running in the virtual mode, okay? When the operating system programs the DMA, it has to give the physical addresses, but the operating system doesn't know the physical addresses. It knows the virtual addresses now. So this IOMMU can handle the DMA. It will help me. It will help me to use the DMA. And interrupts has to be virtualized. Okay, there's an interrupt table. Now that the interrupt table is different for each operating system, right? Our modern IO hardware MMUs, they support the interrupt remapping for each operating system. So virtualization support is something more complicated than just CPU virtualization. Okay, and of course it is not this simple. There are many other details of virtualization, but this is how much I like to talk about. This book talks about the virtualization of the Intel architecture, x86 architecture, but I will not talk into that kind of detail, and that will be basically it. Okay, so this is the end of chapter number 7, and that will be end of the my course, including the makeup courses. Are there any questions? Okay, if you have any questions about the course, about anything, just email me or our TA Ilan, and we will try to help you. Otherwise, I will see you during the final exam. Okay, now, bye.
Thank you for course, sir.
Thank you.
Okay.